Now it turns out, and this is sometimes a nasty surprise, that if you have a constructor for a class that takes a single argument, that constructor will be used to do an implicit type conversion from the argument to an object of that particular class. And this often happens by accident and leads to problems. For example, here on slide 11, we have a function named compare, CMP, and what CMP takes is two arguments, each of which is a reference to a manager const. In the implementation of the CMP function, we're saying, all right, if M1's rate, that is, if M1.getRate, is greater than M2's rate, M2.getRate, then we'll display a message saying M1.getName has a higher rate than M2.getName. This seems quite reasonable. You receive two references to manager const, you compare their rates, and you print out a message if the one on the left has a higher rate than the one on the right. But you may remember that we introduced default parameters into our manager class back in a previous lecture. So the manager constructor that we have now takes a name and a rate and a title and a budget as arguments, but only the name is required. We had default values, 70 for the rate, manager for the title, $500,000 for the budget, and consequently, even though we think of the manager class constructor as having 4 arguments, it can actually be used as a single argument constructor, and here's where that happens. Al is a manager object that we have initialized using all 4 argument values. Name is Al, rate is 55.5, title is boss, budget is $250,000. And above Al we have Bob, which is simply a string initialized from the string literal Bob with a capital B. Now you would think that if I pass Bob as an argument to CMP along with Al, that would fail because Bob, after all, is just a string object. The problem is that our constructor is willing to build a manager object from a string object by applying the default rate, title, and budget. Consequently, we end up with a manager object automatically constructed with Bob as the name, 70 as the rate, manager as the title, and $500,000 as the budget. All right, so the default rate for Bob, for this magically created manager object called Bob, is $70, and so we get a message out on our screen that Bob has a higher rate than Al, because 70 is greater than 58.5. So we may have intended this to work this way, but more than likely it's an error. We can prevent this error from occurring by putting the word explicit in front of the declaration of each constructor that can be called with a single argument. Here we've done this on slide 12, both for the employee constructor, which receives a required name argument but an optional rate argument, as well as for the manager constructor, which takes a required name and optional rate, title, and budget arguments. Once you've declared the constructor explicit, that means it won't be implicitly called like it was here for Bob on slide 11, and instead, if we want to convert Bob to a manager, we have to explicitly call the manager constructor for Bob. So if I just tried to do a CMP of Bob and Al like I did back on the slide 11 program, the compiler would yell at me that I'm doing an illegal implicit conversion. But if I do an explicit conversion by calling the manager constructor directly, this is going to be allowed. And it also, frankly, makes more intuitive sense. Next up, we're going to take a look at runtime identification, so-called RTTI, which makes use of the dynamic cast name type conversion that we introduced a little bit ago. Now, the cool thing about dynamic cast is when you give it a base class pointer as a value to convert, then dynamic cast tests whether this pointer actually points to the specific type of object identified by T. All right? So that's all very theoretical. Let's take a look at a specific example. Over here on slide 15, I have a function named giveRaise, and I'm passing into this function a pointer to an employee. Now, actually, that pointer to employee might be pointing at an employee, or it might be pointing at a manager, or it might be pointing at a CEO. And so this is where dynamic cast comes in. If I say convert PE to be a pointer to a CEO instead of a pointer to an employee using dynamic cast, what will happen is if the kind of object that PE is pointing to is a CEO, then I will get back a pointer to a CEO. But if the kind of object the PE is pointing to is not a CEO, then I will get back a 0. And 0 in an if test means false. Okay, so let's suppose that our pointer to employee really is pointing at a CEO. Then the dynamic cast of the employee pointer to a CEO pointer will succeed. I'll get back a non-zero pointer to a CEO object here, and I can then call the setRate function on this pointed to CEO, and what I'm going to do to set the raise for the CEO is to get the current rate that the CEO has and increase that by 10%. So the CEO gets a 10% raise. Okay, so to skip back to slide 14 for just a moment, if a base class pointer really is pointing at a derived type object specified as your dynamic cast type, then you will get back a pointer to T. Otherwise, you'll get back a null pointer or 0, which will test as false. This process of examining a base class pointer to test whether that base class pointer is pointing at a derived type of object is referred to as downcasting, and this is somewhat frowned on in C++ for various reasons. In other languages like Java, it's the conventional way of doing business, so I'm not going to really express a deeply held opinion about this. Alright, let's suppose that over on slide 15 we get a pointer to an employee passed into giveRaise. We attempt to do a dynamic cast of that pointer to CEO, but this time what that pointer is pointing to is not a CEO. So that's going to fail and give us null pointer, and we drop down to the next if. See, here we have an if that fails, so we're going to say else if, and here we're going to test whether that employee pointer is really pointing at a manager. If that employee pointer is pointing at a manager, then we're going to give the manager a 5% raise over what the manager currently has. Finally, our class hierarchy is only 3 levels deep, so if the pointer was not pointing at a CEO and also was not pointing at a manager, we must be pointing at a regular employee, and so we'll give a 0.5% raise. Obviously, it's better to be a CEO. But this illustrates the idea of what's going on with the dynamic cast. Here on slide 16, we have a program that's making use of a manager object, an employee object, and a CEO object, calling giveRaise on each one by passing the address of each of these objects, and then displaying the new rate after the raises have been applied. So Doug is a manager. When we give a raise to Doug, Doug is going to get a 5% increase, so that's going to be a $3.25 raise. Ed is an employee, so Ed is going to get a 25-cent raise, and Frank, the CEO, is going to get himself an $11 raise. And so the output of our program looks like so. Clearly, you don't want to be an ordinary employee at this company.